So we did a little tiny program and we got some results. That's actually a big step, but I want to go through a little bit larger example. I'm not expecting you to understand everything that's happening in this example. We're kind of going to give you the end view of where we're going to be down the road in a little bit when we can build programs. But we're going to start out with this example so that you can see it all the way through and see some stuff about the tool that we're going to use and how the visualization tool works. So I've actually written a little piece of code, 22 lines of it here, and I'm going to take this and cut and paste it into the visualization tool so that we can work with it. Now you can edit inside the visualization tool as well, and sometimes we're going to do that. But at the moment, let's just pick this up, and I'm going to edit, copy, and I'm going to do, in my case, an Apple V to paste. On a Windows system, it would be a Control V, and on a Linux system, it would be a Control Shift V. But I'm pasting this in, so we've got this piece of code in there to work with and demo this. Let's actually go straight to the visualization execution. And when we do that, this screen comes up. Okay, you can go back to edit the code, you can go back to visualize multiple times, and there's this little red arrow saying this is where we're at. Now, one of the things that makes programming powerful is the ability to reuse pieces of code. And in Python, this reuse thing is called a def, or definition of a piece of code, and we have a name for it, sum list of numbers. Now, it's important as you build code that you give reasonable names to a lot of things, and I would expect something that says sum list of numbers to add up the numbers, and that the thing you would put in it would be a list. So it does something, and we're going to let the Python language process it and take that list and add it up. Now, when we execute this, it actually doesn't run it now. It says, I'm just defining this for later. So it's going to go jumping from here all the way down to line 9. Now there's this thing on line 8 right here. And this thing that says test sum list of numbers is a thing called a comment. The comment does not actually execute. The comment is for the human beings to be able to understand what's going on. As you turn in homework for this class, it's important that you put your name in the comment so I know who the homework came from. The school system that we use, I will get the files and they will be by numbers. And I will say, this is a really nice piece of code. I wish I knew who to give credit for it to, but I don't. So I guess what do I do with it? Okay, it's like, okay, that's good. If you want credit for your homework, you have to put your name in it. And it would also help if you put some other things like which homework assignment it is and some stuff like that. But your name is the critical piece. So you'll want to be able to put in comments. That's an important thing. Line 9 says EXList. And EXList equals this thing over here. First observation. There's an equal sign. And most of you at some point have had some amount of algebra. And I think, usually it is a requirement to graduate from high school that you take at least one algebra class. And in algebra, you have equals too, but they have a slightly different meaning in programming from algebra. In algebra, equals says the thing on the right is exactly the same as the thing on the left. And that's sort of true here, and sort of not true. In a program, usually what equals means is that I'll take the thing on the left, this parentheses 5, 7, 2, none, and all these parentheses, and I will take that and I will copy that, or I will move that into EXList. That doesn't mean I can't change EXList later. And there are languages that do work like algebra, like Haskell and F#. But in Python, it says, take the thing on the right and put it in the thing on the left. So it's actually more like a movement. And we call it an assignment operator. It's not an equivalence operator. So that's what this does. At the end of executing, EXList is equal to the thing on the right. So there is a point in time when they're equal, but it's not like algebra where they're equal forever. So EXList. Now, there's all these parentheses and commas and syntax. We'll see what that does for us in a moment. We go down to the next line that says total equals sum list of numbers. And again, we're going to be creating this thing called a variable in the program called total. And we're going to assign to it whatever this sum list of numbers is. Oh, sum list of numbers is up at the top. It's up here. So it's going to do this. It's going to do a thing called call this function. And it's going to call it with EXList. EXList is going to become a list. And we'll get back to what that does when we actually run it. And then down here we have print total equals. Again, there's a lot of syntax, and you're going to have to learn the syntax. That's kind of like learning the grammar in a foreign language. But here, it says print, and print is a way to get information from inside a program out to where human beings can see it. So it's a convenient thing. It's usually a good idea to print stuff out in your program. Otherwise, you run it and you go, it did something. But what? So we're going to print out this format total. And remember, our comment was we're going to test. So down here, this entire piece down here has to do with testing. And you go, my goodness, what we're testing is the sum list of numbers. And there's more code involved in testing it than there is code in the function itself? Is that weird? And the answer is actually no. If you look at things like the source code for Python itself, or the Go programming language, or maybe the SQLite database, all of them have way more stuff in the testing than they do in the actual thing, because they want to make certain it works correctly. In fact, if you looked at something like SQLite, there's 120,000 lines of code and 3.7 million lines of test cases. So that's where most of the work is not in the code, it's making that the code does what it should do. And realistically, as a programmer, that's what you spend most of your time doing. You build a piece of code, and then you got to make certain it actually does what's in the concept in your head, not what you typed in. Computer programs are the ultimate literalists in the universe. They do what you tell them to do and nothing more and nothing less. So if you tell them to do something wrong, they do it. They don't have any bad feelings about it. They just do it. And when it's wrong, sometimes it comes out very badly. Just ask Boeing and their 737 MAX. You tell it to do the wrong thing, and guess what? The plane crashes. So getting it right is really, really important. So testing is the key piece to that. Let's actually run this and see what happens. Okay, I'm going to click next and we're going to run this. And the first thing you see is on the right, there is this frame and these objects. And the frame is the set of stuff that has your values in it, the names of your things. And the objects is where the value is stored. And the first thing that it created was this thing in your frame called sum list of numbers. Remember, I said define is going to associate a name with a set of piece of code. And that's a function. So it's got sum list of numbers points now at this function. Okay, whatever a function is. And we're now down here, the little red arrow moved to EXList. We now have a little green arrow that says this is where we were, this is where we are now. We went past this comment. I'll step again, and we go to the next line. So apparently EXList, when it runs, it created a variable in your frame called EXList right there. And it has these things called tuples. And a tuple is a pair or more of values. In our case, the first thing in the tuple is a number, 5, 7, and 2. The second thing seems to be this little thing with an arrow that points at the next tuple. This is actually going to turn out to be a list of things, which is good because sum list of numbers takes a list. So this is how you create a list in here. The thing to notice is at the end of the list, there is a none. So there's something that stops the list from continuing forever. So total, sum list of numbers. And now I'm going to click next. And when we went to do total and get the value for it, to do that, we wanted to sum the list of numbers. And guess what? We have a function that does that, but it's up here at the top. Now, it took EXList and it passed it as a parameter, so it substituted it in for a list. And over here in our frames, you'll see that the highlighted frame now is no longer the global frame, it's sum list of numbers frame. So sum list of numbers a list points at the same place as EXList. And we can see a little pointer there. Now the first thing it does inside this function is it says, if not a list. I don't know what a not a list is yet, but we will get to that and we will find out before we are done. So whatever it is, when I click next again, it skips past it. Now ifs are a thing called a conditional logic. If it says, if this thing in here is true, then do the stuff on the inside. But we skipped over that and we went to this line on line 4. Now, Whenever you see something in Python that has a parentheses and a set of stuff and a close paren, it's saying, take the thing on the right apart and put it into this form where I can name the different pieces. So F is going to become the first piece, 5, and rest is going to become whatever is in 1, the rest of the list over here. And then it says return. If you don't return anything from your function, you get nothing back. But in this case, we return something. And hopefully we're going to return 5 plus, well, we have a list, called rest. And in that list called rest, guess what? We've got a function that adds up a list of numbers. Let's call it. So we'll take 5 plus this function. And by golly, that's what it's going to do. It's going to call this function some list of numbers with rest. Rest is the end of the list. And, when we call a function, we go to the top of the function and start executing. So down here, the function called itself, and it created a new frame on the stack. That frame now has a list pointing at this piece over here, this list of 7 and 2 and none. Now, what happens? We go down and say, if this is not a list. I still don't know what a not a list is, but we will still find out eventually. And we want to split up this list so we get the 7 where we can access it. And guess what? We got the 7 into F. Notice that this 7 in F is not the same as this 5 in F in a previous frame. We now have in this frame 7, and we have rest pointing at the 2 and the none. And if we have a list composed of this node in the list, 2 and none, what shall we do with it? Well, I'd like to have the sum of it. Let's find out what we do with it. Let's sum it up. Good. Well, to sum it up, we have a function called sum list of numbers. We pass it a list, and we pass it this little list with just one thing in it. Okay? We come down and say, well, is this list nothing? Whatever that is, it still isn't that. We still want that 2 out where we can get to it. So we'll split it up into the 2 and whatever a none is. And we're going to put that in there where we can add up the 2 and the none. And we have this, I don't know if it's a list or not, but we're about to find out. It's a none. And we're going to add up this none. Okay, so remember, a list is now none. Every time before this, it's been pointing at a list. This time, we come and we say, if not a list. I wonder if this is a not a list. Well, it doesn't have any nodes in it. And guess what? Unlike other times, we're coming to the return 0. None is a special list with nothing in it. And if I wanted to add up no numbers, what would the value be? I'm not adding anything up. So the sum of nothing would be nothing, and we return a 0. And this is the first time we're going to return from this function. And you'll notice that something happens. We're right at the return. We get this little red arrow scooted down just a teeny little bit, and it says the return value is 0 at this point. So where did we call it from? Well, we called it from this place where sum list of numbers was called, with a return value of 2. Okay, because we've added up 2 plus 0 is 2. So the return value here is 2. And then we go next. And it seems like it didn't move, but you notice one of our frames disappeared. And now we're taking 7 plus 2 is 9 for a return value. And we return again. Another frame is gone. And we've taken 5 plus 9, giving us 14. And then when we return this last time, remember we started out with total was the sum list of numbers of 5, 7, and 2. We're expecting to get 14. And now we see in our frame we have a 14 for a total. Now, it's nice when computer programs print something out so you know what they did, because otherwise it's kind of just a magic box, and this time it prints out total equals 14. That's a good result. And now we come to the stuff to evaluate our test automatically. And this is written on the assumption that you're going to run a whole bunch of different tests, but our first test case is really all of the stuff that we do from lines 9 through 16, where we set up a value, we called our function. Normally in a test case, we take out this print statement on line 11 if we're just automating the test. We just want to see if it passed or failed. But in this case, we've got the print statement in there. We saw that, and it printed out the total equals 14 right there. But we haven't had any errors yet, so we're going to make the assumption in our test that the number of errors we've seen from testing is 0. That's really for when you do more than one test. So in our global frame, we've set number of errors to 0. We now say if the total is not equal to 14. So 14 would be success, and if it's not success, then I want to say, by golly, I got an error, and count it. So it is equal to 14. It skips that over. You'll notice that exclamation equals, I call a not equals. And down here we say, at the end of our testing, we're going to say if our number of errors is greater than 0. Well, what's our number of errors? It's 0. So it's not going to do this print statement here. It's not going to do this one. It is going to do the print statement. It's going to go down to the else, where it has false things, and that's actually going to print out pass. So let's see it do that. We got to the print pass, and our test passed. Now, there are a bunch of things in there. There's all sorts of syntax that we're going to have to learn. And there's all sorts of steps. And we're going to come back through the testing because it's really important multiple times. And I started you out with a complicated example that actually does a bunch of different stuff. And I'm not expecting you to understand that example. I'm expecting to say, here's the example. Now let's break this example down into pieces and work through every little piece in the example and learn all the things that are going on. Because I've got a whole bunch of different stuff going on in this example. But this gives you the little bit longer term view. Now as we break it down, you can go back to the example and say, yeah, we saw this in the example. Now I understand how and why that piece was built. And I'm understanding more and more as I'm going through it. But this gives you the starting point for this example. Now you'll notice in this that there's also a previous button. Every time I hit next, it stepped forward. But I can also go backwards. That took away pass. You notice now the arrow is here and it's moving backwards through the code. One of the nice things about this visualization tool is we can actually go backwards through stuff as well as forwards. So I can go back and I can look at the return value again, and then I can step forward through stuff and see it happen again. So I can walk forwards and backwards. And there are some other capabilities in this tool that I'm going to show you as we're working through it. But this gives you the ability to look and see what is going on inside the program. See the pieces and how they interact together. So you can go, oh, I'm seeing that this happens, and this builds my mental model, which is what we're after, of the way programs actually work. Because when you understand how they work, then you can start building code to say, okay, now I have a model of how the computer works. I want it to do this. And when I put in a piece of code, it being the total literalist, it didn't do that. And you go, oh, what do I do now? I start testing it. I start debugging it. I start working through what it didn't do. And I say, okay, I got partway through my code. It did this much of it the way I expected. But this piece down here doesn't work. And you keep successively refining it. And that's how you build a big program, is you take a bunch of little steps. You start building up the steps and testing them from the bottom up with a concept of, at the end, I want to go from this big step down to this other stuff. And in between, I've got to have all these pieces interact and work together. And I test the pieces, I test it collectively, and when I get done, I'm successful and I've built something wonderful. So that is kind of an overview of the visualization tool with our first example really in the tool.